I'm Daniel Stonecipher with Engineering Trust Boundaries and a board member and advisor of the IT community of IFMA. We welcome you all to day 3 of FM Tech Week 2026, presented by Schneider Electric. This session is brought to you by ClimaMind. It's my pleasure to introduce Chuan as he takes us through this insightful session titled Reducing HVAC Energy Costs Without Replacing Existing Building Automation Systems. I appreciate everyone joining us from around the world today. Let's jump straight into the conversation, Chuan.
Daniel, thank you for the introduction, and thanks everyone for joining. I'm Chuan, founder of ClimaMind. ClimaMind helps commercials and industrial facilities to reduce HVAC energy usage by 15 to 25% with AI. For today's section, I will start by playing a pre-recorded presentation video so we can keep the content clear and well-structured. Before the video starts, the host will launch a quick poll on screen. Please take a moment to fill it out. After the presentation, we will come back for FAQ, and I'll be happy to answer any questions. Now I'll go ahead and start the video.
Facility managers are asked to solve energy problems from every direction. Sometimes the chiller plant feels undersized during peak weather. Sometimes it feels oversized because the building no longer operates the way it did before hybrid work. Some days the pressure comes from carbon goals. Some days it comes from utility cost. Some days it comes from a simple question from leadership. Why is this building still so expensive to run? The difficult part is that most familiar answers quickly become capital projects. Replace equipment, upgrade controls, add meters, bring in engineering studies, recommission the building, redesign part of the plant. All of those can be valuable, and many buildings eventually need some of them, but they are slow, expensive, and hard to approve. So facility managers often end up making the same case again and again. This project will save energy, reduce risk, and improve performance, but it needs capital approval. It has to compete with every other budget request in the organization. That is where I think the conversation should change. Before every HVAC improvement becomes a major capital project, facility teams should ask whether there is a software-first path. Can the building use the BAS it already has, the data it already collects, and the equipment already installed, and operate closer to what it actually needs? If the answer is yes, the first step can be smaller, it can be faster, it can carry less implementation risk, and it can prove payback before the organization commits to a larger retrofit. To see why, picture a building that looks like it is doing everything right. It is a large office building on a hot summer day. The lobby is comfortable. Tenants are not calling. The BMS screen is green. The facility team has done its job. Keep the building stable, keep people comfortable, and avoid surprises. From the outside, nothing is wrong. But now look one layer deeper. At 2 p.m., the building is close to peak cooling demand. The sun is strong, people are in the offices, conference rooms are active, and the cooling plant is working hard. A conservative operating posture makes sense. The plant needs margin. Pumps need to move water. Nobody wants a comfort complaint in the middle of the afternoon. By 4:30 p.m., the building may still look perfectly normal. Temperatures are in range, no alarm is demanding attention. But the real building condition has changed. Some floors are emptying out. Internal heat has started to fall. The sun angle is different. The building still needs cooling, but it usually does not need the same cooling effort it needed at 2 p.m. In many buildings, the system does not fully make that shift. The plant keeps operating as if the hardest hour of the day is still happening. Nothing looks broken, comfort is still fine, but the building is quietly spending more energy than it needs to spend. That is the problem hiding in plain sight. Most buildings are not short on equipment. They are not short on dashboards. Many already have trend data, schedules, alarms, control logic, and experienced operators. The issue is not that the building is unmanaged. The issue is that safe operation is not the same thing as continuously optimized operation. That distinction matters because HVAC is usually the largest controllable energy load in a commercial building. If the system runs conservatively for thousands of ordinary hours, small missed decisions become real money, real carbon, and real operating cost. For facility managers, this is frustrating because the waste is not obvious. It does not look like a failed motor or a leaking valve. It often shows up as a utility bill that is higher than it should be, even though the building is being run responsibly. So the question for this session is simple. How do we help an already well-run building operate closer to what it actually needs without risking comfort, bypassing the BAS, or creating more work for the team? The reason this is hard is that HVAC is not one machine making one decision. Stay with the same building. In the morning, the building wakes up before people arrive. Air handlers start. The plant comes online. Temperatures are pulled into range. By the time occupants walk in, nobody notices the HVAC system. That is the goal. But behind that quiet morning, the system is making decisions all the time. How much cooling should we make? How much water should we move? How hard should the fans work? How much margin should we keep because the day may get warmer or the building may fill up? Those decisions are connected. A setting that helps the chiller may make the pumps work harder. A cooling tower decision may reduce one kind of energy but increase another. A zone level change may reduce demand, but only if comfort stays protected. The useful picture is a relay team. The room gives heat to the air system. The air system passes that demand to chilled water. Chilled water brings it to the plant. The plant pushes it outside. If one runner changes pace, the rest of the team feels it. That is why manual optimization is hard. The facility team is not tuning one device. They are managing a chain reaction. The real question is not, can this one device use less energy? The real question is, can the whole system serve the building with less energy right now without creating a problem somewhere else? This is also why writing more fixed rules is not enough. If the problem were simple, we could write rules for every condition. If it is hot outside, do this. If the building is half occupied, do that. If one chiller is running, use this sequence. If two chillers are running, use another sequence. This is how many good buildings already operate. They have schedules, sequences, set points, and overrides. They may also have periodic commissioning or retro-commissioning work that brings the building back into a better state. All of that is valuable. None of it should be dismissed. But those methods are still mostly static. They capture what the team knew at the time the sequence was written or the building was tuned. They do not continuously ask whether the current hour is different from the hour the rule was designed for. But the number of situations grows very quickly. Morning is different from afternoon. Humid days are different from dry days. A tenant event, maintenance activity, or weather shift can change the right answer. And HVAC decisions do not show their full effect immediately. If we change pump speed, water temperature, equipment staging, or tower behavior, the building needs time to respond. So the question is not only what should we do now? The question is, if we do this now, what will happen over the next few minutes or the next hour? That is why buildings naturally drift toward conservative operation. Designers size for peak conditions. Contractors commission systems to meet requirements. Operators tune systems to avoid complaints and alarms. Facility teams are judged first on whether the building works. Conservative operation is not a failure. It is rational. It is often the right default. But it also leaves savings behind. The uncomfortable truth is that good operators are often careful operators. They know the cost of being too aggressive. So when there is uncertainty, the safe choice is usually to keep more margin. That is exactly why this problem needs a different tool. We are not trying to make operators less careful. We are trying to give them a way to be careful and still find efficiency. The building keeps carrying old assumptions. It carries the morning assumption into noon. It carries the 2 p.m. assumption into 4:30 p.m. It carries the worst hour assumption into ordinary hours. That is the need, a way to keep the building safe while helping it stop acting like every hour is peak load. This is where AI control becomes useful, but only if we frame it correctly.
AI should not replace the BAS. It should not become the safety system. It should not make unexplained changes that the operator cannot see. The BAS, local controls, PID loops, alarms, and equipment safeties remain the foundation. A better way to think about it is this. Traditional control keeps the building inside the lines. AI optimization helps decide where inside the lines the building should operate. For ClimaMind, the practical question is simple. Can software help the existing BAS make better operating decisions without turning the project into a large retrofit? That is why we call this a software-first solution. The software layer sits above the BAS. It learns from operating data, weather, load patterns, meter behavior, and facility constraints, then helps the building move safely to better operating points.
That matters because the economics are different from a capital upgrade. The first step can be small. Connect to the existing BAS, define the approved control surface, run advisory validation, and measure whether software control reduces energy while keeping comfort protected. When that scope is right, implementation can be short. The risk is lower because the existing BAS remains the fallback. The cost can be low enough to fit a facility-led pilot, often in the low tens of thousands, rather than a major capital project. And because the system is acting on operating decisions, payback can be evaluated quickly against real energy data. Our AI solution can learn which small operating moves tend to help, which moves should be avoided, and how the building responds over time. The training and validation happen before broad control authority is granted. Production control stays bounded.
In technical terms, this is reinforcement learning applied to HVAC control. In business terms, it is a software layer that learns a better operation strategy before it is allowed to control anything broadly. Local controls still maintain temperatures, pressures, alarms, and equipment protection. The software layer makes higher-level operation decisions. Given what the building needs now, where should the plant operate inside the safe space? That is why we put several safety layers around the AI. First, advisory validation. Before control is enabled, it shows what the AI would have done, what effect it expects, and why the move stays safe. Second, hard safety boundaries. The team defines what AI can touch, what range each value can move within, and what conditions stop optimization immediately. Third, small step tuning. The system does not make dramatic jumps. It makes small changes, watches the response, and only continues when the building stays healthy. Fourth, AI BAS handoff. The BAS remains the operational foundation. If the AI layer is paused, loses confidence, sees a fault, or crosses a stop condition, control hands back to the existing BAS strategy. AI becomes operationally acceptable when the control path is visible, bounded, measurable, and reversible. It also avoids extra work. Advisory validation builds evidence and trust. Once the strategy is approved, AI can make small judgments inside the approved space, while the team keeps policy control,
visibility, pause, override, and handoff.
Human in the loop is a trust-building path, not a transfer of responsibility to the facility team. AI should explain each action, what it would do, why, the expected effect, and the safety boundary. As the system proves itself, the team can allow more autonomy. We have confidence in our AI, and we support facility managers building that confidence step by step. ClimaMind remains accountable for the AI control layer we deploy, its boundaries, monitoring, performance, and safe handoff. Now, let us make this concrete. A first customer collaboration should feel like a focused operating pilot. That is important because the first question from a facility team is often not technical. It is practical. How much work is this going to create? How much risk does it add? How long before we know whether it pays back? A software-first project should answer those questions directly. Narrow scope, existing BAS, approved points and ranges, lighter installation, low tens of thousands cost, and results evaluated quickly against real building data. We start with the data the building already has. Before controlling anything, we look at historical BAS data and learn how the plant normally behaves, when demand rises, when it falls, how the plant responds, and which operating ranges the team already considers acceptable. This first step grounds the evaluation in the customer's building, history, equipment behavior, and constraints. Then we install our compute device alongside the BAS. The BAS remains in place. The existing control strategy remains available. Our layer observes, optimizes, and only works inside the scope the team has approved. For the building team, the project begins with visibility. What does the plant normally do? When does it become conservative? Where does the team already know the building is sensitive? In one cooling plant project, the first question was very practical. If the BAS would normally run the plant one way, how would the AI run it differently? And would that difference still stay inside comfort and equipment boundaries? The first verification focused on control behavior. Which equipment would be adjusted, how far the adjustments would move, and which limits the AI would respect. The team could see optimization as a series of small, bounded decisions. The team should be able to understand the behavior in plain language. This is the equipment group we touch. This is the range we stay inside. This is the condition that stops us, and this is how control hands back to BAS. Then we measured the result in the simplest way possible. For the same cooling service, did the plant use less electricity? During one measured AI operating window, average plant efficiency improved from 0.74 to 0.65 kilowatts per ton, or 12.11%. The method matters. Show how we would control, keep boundaries clear, protect operation, and compare energy use against normal operation. That is the proof pattern. Focused scope, clear control boundary, simple energy metric, and before and after comparison. Picture what this feels like for the facility team. The building remains comfortable. The BAS still does its job. Operators can see the range, the control moves, and the handoff path. The energy review is no longer a vague discussion about whether AI works. It becomes concrete. Here were the hours. Here was the cooling service. Here was the energy use. Here were the boundaries, and here is what changed. For facility leadership, the value is also practical. This is not another open-ended retrofit. It is a controlled operating layer that can be observed, limited, audited, and reversed. For owners and operators, the value is a portfolio that learns. One building teaches where the opportunity is. The next building starts with better knowledge. That is what better operation looks like. Not drama, not disruption, not a dashboard that creates more work.
just a building that quietly runs closer to what it actually needs.
So, how should a team start? Start small, but make the first step real enough to measure. The starting point should be a clearly bounded HVAC operating scope, specific enough for the team to understand what could change, what stays protected, and how results will be measured. The first step is simple. Use the building's existing data to establish a baseline. Learn when demand rises, when it falls, how the system responds, where comfort is sensitive, and where the building has flexibility. Then define the pilot like an operating project, not a capital project. One bounded scope, a small group of approved control points, a clear stop condition, a clear handoff to BAS, a short measurement window, a budget that can often sit in the low tens of thousands instead of a major equipment approval. Then use advisory validation to show how the AI would control before enabling control. The team sees what would change, why it stays within boundaries, and when the system would stop. Only after that does the scope move toward limited closed-loop control. Approved systems, approved points, approved ranges, approved conditions, clear handoff back to BAS. That sequence builds trust quickly. Facility teams understand the behavior, operations understands the handoff, and leadership can decide whether the next step is justified by evidence. The first operating window should answer a few practical questions. Did the control strategy make operational sense? Did comfort remain protected? Did energy use move in a measurable direction? Did the team feel comfortable with the boundaries and handoff? That is a low-risk way to bring AI into building operations. Keep the BAS, keep the boundaries visible, avoid endless manual approval, and in many organizations, start below a CFO-level capital approval. It asks a simpler question. Can we prove that this building can deliver the same comfort with less energy inside boundaries the team understands? If we can prove that, the next step is not a leap of faith. It is a business and operating decision based on evidence from the building itself. That is why software-first optimization should be one of the first options facility managers consider. It is fast to test, lower risk than a retrofit, easier to pause or reverse, and tied directly to payback evidence. For facility leaders, the value is a better way to manage a complex system without adding more burden to the team. For owners and operators, the value is measurable energy improvement that can become portfolio knowledge. The goal is simple. Keep the building comfortable, keep the team in control, and use less energy when the building gives us the opportunity. That is the practical path for AI HVAC control.
All right, here's the end of presentation, and the host will show you a poll on what you think of the presentation. And do we have? I know it's also a great time for you guys to put in any FAQ questions, so I can answer. So the poll is what will be most likely for you to pilot a HVAC optimization solutions, and we want to know what will be very important for you to hear. So the solution, thanks William for the question, how long does the solutions to take into implement? Because this is a very lightweight software solutions, it takes less than a month. So as I previously mentioned in the presentation, there is no hardware retrofit at all. Well, there's very little hardware retrofit in place. So all we required is to put computing devices right next to BMS and connect that. And the rest is basically done by software, which happens very fast. So within a month, you will be able to see the actions the system going to send, and you're going to see the actual results. Right. Another question is the purpose build AI or develop a general platform? It's a purpose build AI. So we use reinforcement learning to train our model from start. It's not a standardized LLM. It runs on real HVAC systems operation data instead of language that is vague and unpredictable. So it's very accurate. It's like paid chess accurate. That give you actual actionable command and make sure the system runs efficiently. Right? Is there any more questions here?
Okay, great. If there's no more questions, you'll all be able to find the recording on the FM Tech Week 2026 website. That was a great presentation, Chuan. Thank you so much for sharing more about ClimaMind in your AI systems. Certainly a very hot and interesting topic in the world today. I appreciate everyone joining us today and look forward to seeing you during our next FM Tech Week session at 10 a.m. Pacific time with Joseph Betcher and Romina Koss from Desk Pilot. Thank you all and have a great day.